Hi, welcome back. Today we're going to take a look at more practice with writing vector equations of a line in 2 and 3D. So let's take a look at a review real quickly. So let's say we're given these points A, B, and we're given a directional vector. I changed that to UV, this way we don't get confused with the X's and the Y's. And we want to write the vector equation of that line. Of course, writing the vector equation, we're going to write this as x, y, equals, and remember this is kind of like our point slope form, so we start off with the point that we have, this AB, plus t, that's kind of like your variable there, your independent variable for the parametric, multiply that by your direction vector, UV. We're in our room there. And that would be the vector equation of our line. So here we have a line in standard form, x and y, and we're asked to write the vector equation of the line. Now, remember, we need a starting point, and one of the quickest ways we can find a starting point is to use the x or y intercepts. Since it's a line, you can use any point on the line, but the intercepts are a little bit easier to find. So, to write the equation of my line, the first thing I need is a point, just like we did in Calculus BC. And I am going to find the x-intercept. So if I let y be 0, our x value becomes 6. Next, to write any vector, the equation of a line, of course, we need our slope. And if I find the slope here, if I solve this equation, my slope is going to be, if I bring the x over, this becomes -2 divided by -4, so 1/2. Now that's my slope. Earlier we talked about how to write this as a direction vector. Remember, the top is my change in y, the bottom is my change in x. So my direction vector will be 2, 1. My change in x followed by my change in y. And then we can write the equation of our vector equation of the line. Remember, it's xy equals our starting point, which is going to be the 6, 0 plus t times 2, 1. Now, if you use the x-intercept, you'll have just a different point. I'm sorry, the y-intercept, you'd have a different point than me. But you could let x be 1, and you can solve for y as well. So there's our vector equation of our line. Now, you could have another answer, xy equals, same thing, 6, 0, plus, and you can even have it go in the opposite direction. And that would be okay as well. Because remember, the slope, if I want a slope of 1/2, I could also write this as -1 over -2. Still a positive, so we can have it even have in the opposite direction. And that's where this one travels, in the opposite direction. When you're writing the vector equation in 3 space, or 3D, the equation of a line, we have the same equations. X, Y, Z, our starting point, plus t, which is our independent variable in parametrics, as well as this A, B, C right here, which is our direction vector. Still. This is in 3D. If you want to write this as a parametric, we would say x, for the x's, x would equal x naught plus at, y would be y naught plus bt, and z would be z naught plus ct. And these are our parametric equations for our vector equation of a line in 3D. And from parametric, we talked earlier, we can write these in the symmetric form of a line. Remember, to write the symmetric form of a line, we just solve x for t, y for t, and z for t, and that's what we did here. So we got t equals x minus x naught over a, t would equal y minus y naught over b, t would equal z minus z naught over c. I just solved each one of them if I solve for t here. And in solving, and since they're all equal to t, we can just set all the corresponding parts equal to each other. And this is our symmetric form of our line. Now notice the point, or the initial condition, is on top. That's our x naught, y naught, z naught. On the bottom, we have our direction vector. and that's our A, B, C. So if you just know what x naught, y naught, z naught are, and you know your direction vector, you can go pretty much straight to any form that you want. And that's what we're going to be taking a look at here today. So let's take a look at an example. We're on part 1 here in this example down here. Then we'll take a look at some other problems on the back. So, and now, almost forgot to mention, if any of the constants a, b, or c are 0, we omit that equation from the equality. We're going to see an example like this. This is actually very important, and it's the one that most of us tend to forget. So here we're given two 3D points. We want to find the following: the vector equation of the line. So the first thing we have, I have a point. I just need our direction vector, and that's pretty easy to get. Direction doesn't really matter in this situation right here, so I'm going to go 1 minus 1. 1 minus 1 is 0. 2 minus a negative 2 is 4. 5 minus 3 is 2. Remember, direction doesn't matter because, kind of like we did up here, where we have the slope, both positive, both negative, so it's the same slope there. So when you write your direction vector, you can have it. You can actually go the other way. You can have 0, negative 4, negative 2 as well. So the equation of a line with 3 space will be x, y, z equals my starting point 1, negative 2, 3 plus t, my independent variable, 0, 4, 2 for my direction vector. To write this as a parametric equation, x would equal 1 plus 0t, or just x equals 1. Note, a here is 0. That's going to be part of a problem right up there, which we'll get to in just a second. Our y would be negative 2 plus 4t, and z would be 3 plus 2t. And there's your set of parametric equations. Now, if I want to write these in symmetric form, I could solve for t in each one of them, and it's not that bad to do. Up top here, though, for x is still going to be 1. We'll talk about that. Solve for t here, t would equal y plus 2 over 4, and t would equal z minus 3 over 2. Now, I could just use my formula for symmetric form and memorize that the point goes on top and the bottom is your direction vector. But writing it out this way is not that bad. It doesn't take too long to solve it algebraically. So in symmetric form or rectangular, we would get, now notice, I'm going to leave this alone for now because there's no t now on this one, so I can't really compare it with these two. So we say y plus 2 over 4 equals z minus 3 over 2, and at the end, a comma such that x is 1. So what this is telling us, this is the equation of a line. This is a line in 3 dimensions where all x values are just 1. So the x values never change, and that's what that means for us right there. And the last question says, would this line pass through the xz plane? Well, to find out if it passes through the xz plane, we need 2 points. I need to solve for x, y, and z. Well, we already know x is 1. So I'm going to pick a random y value. Easiest y value I can do, pick 0. So basically you pick 2, solve the third. So if I know x is 1, and if I pick x is 1 and y is 0, if I plug it into my equation, I can get 0 plus 2 over 4 equals z minus 3 over 2. And I can just cross multiply. That's going to become 4 equals 4t. Whoops, that's if we were looking z, almost looked like a z there. 4z minus 12. And if you solve that, z equals 4. So yes, this will pass through the xz plane. It will pass at this point. It will pass through the point x is 1, x is 1, y is 0, and z is 4. Now, again, I kind of maybe misled you. Again, the reason why we pick y as 0, if I'm looking for the xz plane, y is 0 at the z-plane. So I know where it all lands now. Anyway, so that's the end of part 1. So if you enjoy this, go on to part 2. We'll do some more. Bye.